All right, we are going to jump right into our topic on buffers today. If you did the POGL and you watched the 2 videos I posted, you kind of have an idea already of what a buffer is. That is, this is a solution that has a weak acid and a weak base present in it that are conjugates of each other. And because both are present, they resist changes in pHs when acid or base is added to the solution. If you watched the 2 videos, you saw, this is pretty applicable in our daily lives. Paul Anderson in the Bosman Science video talked about how our blood has a buffering system involving carbonic acid. In the crash course video, you saw him talk about how the rivers in Montana are able to resist, changes due to acid rain because of the calcium carbonate present from the limestone. So while we're talking about this and doing the calculations, just keep in mind this is, again, something that kind of occurs all around us in a lot of different ways. So let's jump in. I'm going to calculate the pH of a buffer solution with you. I'm going to show you 2 methods, the ice or rice table method, and then what I'm going to mostly focus on is the Henderson-Hasselbalch equation, but I'll show you both to start, and then we'll talk about some calculations when you actually have an acid or base that's been added to it. So for this first one, let me just get this ready. We're going to just start off with the reaction in the ice table just so you can see how this ties into what we've already done, and then I'll show you the Henderson-Hasselbalch equation. So for this one, we have our acetic acid. Think about from our Ka. That's going to donate a proton to water. So we have our acetate ion, which is its conjugate, which can act as a weak base, which it will, and then the production of hydronium. Now for this one, we're creating the buffer system, so we actually have initial concentrations here. We have the 0.3 molar acetic acid, and then the acetate ion is present from the sodium acetate solution. So really, it's this acetate ion, which is going to act as the weak base, which is just the conjugate of the acetic acid. So we're starting with 0.3 molar. And we're going to say that there's no hydronium present because that amount from the autoionization water is going to be much less than 5%. Now, because the hydronium is 0 there, we know this is going to proceed towards the right to establish equilibrium. So this will be minus x, and then these guys will be plus x's over here. So I can simplify that. And x over here. So then we're going to use our Ka expression because they gave us the Ka is 1.8 times 10 to the negative 5, and then concentration of our products over our reactants, and it's all 1-to-1 up here. All right, and then just like when we were dealing with weak acids in our last unit, we're going to simplify this down, which you can go ahead and check it at the end. For time, I'm not going to show you the less than 5%, but it does end up being less than 5%. Because of them having equal molarities, we're going to see that X, which is equal to our hydronium ion concentration, is the same thing as our Ka value. Now, don't stress out too much about sig figs. In all honesty here, you probably want to use the 3 in the given molarities that they gave you, but if you end up using the 2 in Ka, that is the constant, you're fine. So just to do the 3 here, you would end up with 1.80 times 10 to the negative 5th for your molarity. And then if you take the negative log of that, your pH, so 8 times, negative 5th, and then taking the negative log of that, you get 4.7 if you're doing 3 sig figs for 5. Okay, or if you had it to just the 2, you would have 4.74, just based on the number in the calculator. So just be aware of that. Now, that's one way to go about doing these. The other way for buffer solutions that's great is that we have the Henderson-Hasselbalch equation that we can use for our buffer solution. And this is right in your AP reference tables. That'll jump over to. So right on the front, right under equilibrium, it's this one right down here where it says the pH is equal to the pKa plus the log of the conjugate base concentration over the weak acid concentration. So that is our pH is equal to the pKa of the weak acid plus the log. And for us, I'm going to actually use the acid, the acetic acid concentration has to go in the bottom. And then up top is going to be its conjugate base, which is going to act as our weak base. Okay, so our pH is equal to, now it might be a little while since you've thought about this, that for our pKa, that is equal to the negative log of our Ka. Okay, so when you plug that in, you're going to see for this one 4.74, and that's just keeping with the 2 sig figs in the constant there, and then plus the log here. So same idea, we're going to use our concentrations. So we have our 0.3 molar of our acetic acid that's going on the bottom here, and then we had 0.3 molar of our acetate ion, which is going to go up top here. Okay, because these end up equaling, 1, we would have our pH is equal to the same as our pKa. So 4.74. Now, if you wanted to keep the 3 sig figs, of the 0.3, you could throw in a 0 at the end to make that have the 3. It's going to stress you out. So 2 ways to do it. Obviously, you can see the advantage of the Henderson-Hasselbalch equation is speed. It definitely helps with, but I did want you to at least see how this relates to our weak acid and weak base calculations from our last unit. But I'm going to focus on using the Henderson-Hasselbalch equation as we move forward. Okay. All right, if we look at number 2, now in number 1, the concentration of the weak acid and weak base were the same. So our pH was equal to our pKa. So when they are not equivalent, we're going to see that that relationship no longer exists. So here we have our pH is equal to our pKa plus the log, and then we have our HAC, weak acid, and our acetate ion. Our pKa based off of that Ka is 4.74. And then making sure you're really careful here with where you place in your concentrations. The acetic acid on the bottom was the 0.2. The acetate ion is 0.1 on the top. So when you plug that in, plus the log of 0.1 divided by 0.2, you get 4.439 if you use the 3 sig figs of the concentration, or 4.44 if you use the constant there. Again, some of these answers over on the worksheet were from the ice table, so it might be a little bit different. But that would be the pH of the buffer solution based on those concentrations of the weak acid and the weak base. Okay? All right, so try out 3, 4, and 5 on here. You can pause the video and try them out or go back to it shortly. But I also want to talk about, well, what happens when we do add an acid or base to the concentration. So for number 1, we have acetic acid again. They just wrote out a little bit different. Just so you can see it in front of us. So we still have the production of our acetate ion and hydronium. So for this one, I'm just going to jump right in to show you, which we really already have done this. So we have our 4.74, which is our pKa of the acetic acid, plus the log of the 0.5 molar concentration of acetic acid over the 0.5, and then above it in the numerator, 0.5 molar of our acetate ion. And we know that when those are equivalent, the pH of the buffer is going to be equal to the pKa, so 4.74. So that's just our initial starting pH of the buffer. So now we're going to focus in on, well, what happens when we add a strong base or a strong acid to it. So for B on here, it's saying we're adding in 0.02 moles of solid sodium hydroxide to 1 liter of the buffer solution. Ideally, you want to use molarities for the Henderson-Hasselbalch equation, but because the volume of everything is going to be equivalent, it's all in one solution, technically the volumes cancel out in this, so you could use moles, but right now we're going to stick with just using molarity. So we have 0.02 mole in 1 liter, so that means then that we're going to have 0.020 molar of sodium hydroxide, which is really our hydroxide ions. So what you need to think about when you get to this point is, what is that sodium hydroxide going to react with in the buffer solution? What's going to consume it? And in this case, we know acids and bases react, so our acetic acid is going to react with the sodium hydroxide. So the reaction that's going to take place is our acetic acid is going to react with the sodium hydroxide. Now I am just going to use the hydroxide ion here. The sodium ion is just a spectator ion. If you want to include it, you can. Just make sure it doesn't affect your calculations somehow. All right, those are going to react. The acetic acid is going to donate its proton to form the conjugate. and then water. So what's going to happen in our buffer is that the acetate, or this acetic acid, sorry, is going to react with the hydroxide. So the acetic acid is going to decrease when the sodium hydroxide is added. Because of that reaction is going to increase the amount of acetic ions in solution, or the acetate ions in solution. Sorry, I'm like mixing these guys up the whole time. So when we go to use our Henderson-Hasselbalch equation, we're going to show that occurring. So our pH is the 4.74 plus the log. Okay, with this, they both start off with 0.5. Now remember, this is our weak acid on the bottom. This is our weak base on the top. So the acetic acid is going to decrease, minus, and the weak base, which is our acetate ion, is going to increase. Okay, always take your time deciding where those are going to go. And then we know that the hydroxide ion concentration is 0.02, so then I will fill in that part, which will be equivalent in each of those. Okay, so then when you do 4.74 plus the log 0.5 plus 0.02 divided by 0.5 minus 0.02. Okay, and with this you could keep, I'm going to just do two sig figs, everything is in two sig figs, that simplifies it. 4.77. And again, this one is really just based on the ice table if we were to do it that way. All right, and that would be our pH. So imagine if you had, and you could do this on your own, the 0.02 molar sodium hydroxide and the pH change from a neutral 7 at 25 degrees Celsius to if you were to place that in pure water. It would be a huge change. Okay, with this, in the buffer solution, it's only going up 0.03 pH units. So again, there's the idea of it's decreasing the effect of the sodium hydroxide that's being added to the pH of the system. Okay, all right, let's look at the next one. We have 0.02 moles of the hydrochloric acid in 1 liter. So that means we have 0.020 molar hydrochloric acid. So what is the hydrochloric acid going to react with? It's a strong acid, so it's going to react with the weak base of our system. So the weak base of our system is the acetate ion. And this is going to react with, you can use H plus here, but I don't want it to look too different from the equation above, so I'm going to use the hydronium. Oops, sorry, that should be just a one-way arrow. So the hydronium is going to donate, which again, strong acid, that proton is going to form the hydronium with the water, which will then react with the acetate ion. So we will form acetic acid from this reaction and then water. Okay, so if we look at adding the hydrochloric acid, it is going to cause the weak base in the system, the acetate ion, to decrease. And then it's going to produce more of its conjugate, which is the weak acid, which is your acetic acid. Okay, so when we go to plug this into our Henderson-Hasselbalch equation, okay, remember they're both starting off, and this is like, you know, brand new buffer solution. So we're both starting off with these 0.5 molar of the weak acid and weak base. And again, remember the bottom part here is the weak acid. Oops, why wrote that? And then this is our weak base. Okay, so the acetate ion, which is our weak base, is decreasing, so minus up in the top. And then our acetic acid is increasing, so we're going to do plus on the bottom. Okay, our amount was 0.020. Okay, and if we plug that in to our calculator, okay, and rounding to sig figs, we get 4.71. Okay, so again, if we think about if we were to add in 0.02 molar hydrochloric acid to pure water, the change from a pH of 7 to adding in that acid would be, you know, huge compared to the fact that this only decreased by 0.03 pH units. Okay, so it buffered the change in pH. It worked to stabilize it. It didn't have as big of an effect. Okay, all right, so make sure you try out 2, 3, and 4, and we will check in with this and move on to part 2 in our next video.